All right, Algebra, Chapter 10, Lesson 2. Okay, here we go. Lesson 2. This is called Simplifying Radical Expressions, and honestly, I gotta say, this is one of my favorite things to do in algebra. When they say simplify, they mean they're gonna have something like the square root of 20. And I understand that you can just plug that in your calculator and you can get, whatever that is. What is it? It's between 4 and 5. You can get 4.3 something, whatever. But they don't want that. When they say simplify, it's kind of like reducing in fractions. So if you got 6/10, they're not asking you to turn that into a decimal or anything else. They're asking you to kind of reduce it. Well, with simplifying radicals, what we're going to do is we're going to take out any perfect squares. And we're going to get those out of the radical sign. Remember, perfect squares, think 1 times 1 gives you 1, 2 times 2 gives you 4, 3 times 3 gives you 9, 4 times 4 is 16. So perfect squares, you know what those are. So we're going to look in here, and we're going to see if there's any perfect squares, and we're going to get them out of the radical sign. The other thing we're going to do is we're never going to leave any square root things or radicals as the denominator of a fraction. So let's just go to work. It might sound a little complicated, but trust me, as soon as you do a few, I think you'll find it as fun as I find it. I do it at night, when I wake up, who knows when. Anyway, so the square root of 20, think of the factors of that. You have 1 and 20, you've got 2 and 10, you've got 4 and 5. Are any of those perfect squares? Well, hopefully the last one rang a little bell. I could rewrite the square root of 20 as the square root of 4 times the square root of 5, right? That's the same thing. The advantage of me doing this, though, is that the square root of 4 turns into a regular old number. So now I can rewrite that as 2 times the square root of 5. So does that make sense? I've pulled out a perfect square and I've got it out of the radical sign, and what's left behind is anything that doesn't have any perfect squares in it. And so I'm done. I've simplified this problem. Let's try a different one. What about the square root of 48? Now, it's again kind of like reducing fractions. It doesn't so much matter where you start. It's the easiest, of course, if you can see the greatest common factor for everything, like for fractions, and you pull that out of them, you reduce it by that much. But if you can't see that, you can just reduce it a little at a time and you'll get there. Same thing with simplifying these. So the square root of 48, you could go through in your mind and list all the factors. But I see immediately that there is a square root of 4 in there. Okay, or there's a 4 in there as a factor. So I'm going to rewrite that as the square root of 4 times the square root of 12, right? Well, that's going to reduce to a 2 times the square root of 12. Now, are you done at this point? No, because inside of that, there is another perfect square. So I could rewrite this as 2 times the square root of 4 times the square root of 3. Does that make sense? That's going to change into a 2. So I'll have 2 times the square root of 3. And if I simplify that, it's going to be 4 times the square root of 3. Am I done at this point? Yeah, because there's no perfect squares there. I've pulled everybody out. Now let's go back to our original. If you look at this, there is a bigger factor that's a perfect square, and that would be 16 and 3, right? So if we rewrite this as the square root of 16 times the square root of 3, well, that's going to turn in one step into 4, and then we're left with the square root of 3. So you see we did a little quicker that time. It doesn't matter, you're going to get there no matter what. So when you're faced with reducing, what if they gave you something a little more complicated, like the square root of, what do we have? I don't know, 64 a squared b cubed. Well, we could go through and reduce this. The square root of 64, of course, is going to be 8. The square root of a squared is going to be a. Now, b cubed, think about it. We could rewrite that as the square root of b squared times the square root of b, right? So we can pull the b squared out of there, and we're left over with that. So the square root of b squared, of course, is going to be b. And then the last thing we have left over is the square root of b. Now actually, let me just zoom in here for a second. There's a technicality here that I want to go over real quick. Let me just erase this actually. When you have the square root of something to an even exponent, it technically does not equal itself. Now it can, but there's also possibilities that it can't. Like let's say, what if it was -3? What if a equals -3? Well, think about it. The square root of -3 squared, that turns into 9. The square root of 9 is 3. That equals 3. So in this case, a would equal 3. It does not equal -3. So here's the technicality, and I hate to do this to you. If it's an even exponent going to an odd exponent, then you have to use absolute value symbols around it. Okay? So if it's an even, if it starts off as an even exponent, in this case squared, going to a to the first, then you have to use absolute value symbols. Now if it's an odd exponent, going to an odd, that's totally fine. If it's an even going to an even, that also works fine. Think about it like this. What if it was a to the fourth? Would that actually equal -3 squared? Yes, it would. So if it's an even exponent going to an odd, you have to use absolute value symbols around it. If it's an even going to an even, you're fine. And you would never actually do a square root of an odd, so don't worry about that. Okay? So there's a little technicality. I'm going to throw it in, and hopefully we won't have to worry about it. So getting back to the last one, what you actually should have written was 8, a absolute value of a, and then b times the square root of b. Okay? All right. What if we have a square root on the bottom, for the denominator of a fraction, let's say? What if we had the square root of 12 over the square root of 2? Well, you remember how to reduce this. We did this before. Rewrite this as the square root of 4 times the square root of 3. We can't really do anything here, so we'll leave that as the square root of 2. And then if I rewrite it in a simplified form, it's going to be 2 square roots of 3 over the square root of 2. I'm not allowed to leave that on the bottom like that. So the easiest way to get rid of that, if there was a square root of 2 up above, you could just cancel it, but there's not in our case. So the easiest way to get rid of this is, you see that if we multiply by, you can always multiply by 1. So if I multiply by the square root of 2 over the square root of 2, square root of 2 times the square root of 2 will turn that into a 2, or the square root of 4, which is 2. And this is going to turn into 2, and then the square root of 2 times the square root of 3 is the square root of 6. Now, are we done at this point? I hope you can see that we're not quite done. We've gotten rid of, there's no radical on the bottom, but now there's a 2 that's a factor, and there's a 2 down here, so that'll cancel. So our final answer for that whole thing is going to be the square root of 6. I hope that wasn't too fast for you. Basically, we just want to do anything we can to get rid of that. If we can cancel it, that's fine. Otherwise, multiply by something that'll take that away. And usually if you multiply by the same thing, the square root of 2 times the square root of 2, you'll get rid of that. There's a little more complicated version of this. What if we just had like 2 over 1 plus the square root of 3? This is a little more complicated. We can't simply multiply by the square root of 3 down here. Do you see why? If we multiply by the square root of 3 over the square root of 3, that would be fine up above, but the square root of 3 would get multiplied by the 1, and it would also get multiplied here, which is fine, but now we still have another square root. So it's not going to work just multiplying by that. What we're going to multiply by is what's called the conjugate. We have 1 plus the square root of 3 down here. The conjugate of that is going to be 1 minus the square root of 3. And you'll see why this works in just a second. So let's multiply by the conjugate. 1 minus the square root of 3 over 1 minus the square root of 3. If you remember, this is that form where you have something plus something times something minus something. And that's simply, the quickest way to do that is, well, first of all, let's do the top. It's going to be 2, and then 2 times negative square root of 3 minus 2 square root of 3. The quickest way to get rid of that, or to do that though, is you square the first one. You square the second one, which turns that into a 3. Squaring that is the square root of 9, right, which is just 3. And you subtract. So do you see that got rid of our square root stuff, our radicals on the bottom? If you need to pause for a sec, just pause, but think about this. This is squared, and we subtract. So now all our radicals are gone. And our final simplified version is going to be 2 minus 2 square root of 3 over 1 minus 3 is negative 2. Now you might ask yourself, are we truly done at this point? Well, we're not, because do you see that there's a factor that's the same in each one of those? So, unfortunately, I kind of just picked some numbers that made this a little bit more complicated, but I think you can handle it. Let's factor out a 2 here. So 2, and that leaves us 1 minus the square root of 3. And that's over negative 2. 2 over 2 cancels out. We're still left with this negative sign. So you can leave it like that, or you can turn everybody the opposite here. We don't need this anymore. So that's okay. Or you can multiply that by everybody and make it square root of 3 minus 1. That would also be acceptable. Okay. Hope that made sense. We're going to go over this tomorrow, and I'll see you then.